Hello guys, welcome back to another lesson within Unit 1 of the iGCSE Computer Science syllabus. We are still looking at data representation, and in particular today we're going to look at digital images, following on from the last lesson where we explored how digital audio is represented using binary, and today we're going to look at digital images. So very similar to the last lesson, we are going to look how and why a computer represents an image, including the effects of these two terms, resolution and color depth. So very similar to audio in terms of sample resolution and sample rate, we've got the terms resolution and color depth when it comes to an image. So just to get us started, what I'd like to talk about is this term pixel. Now it's a term you might have come across before. Images can become pixelated. If you're into games, you can have more pixels in terms of the quality of your game. Or if you're into photography, you know how many pixels might be in an image. But when it comes to what a pixel is, we need to understand that a pixel is a tiny dot. So one of the squares here represents a pixel. Now this is important because when it comes to each pixel, we're going to go into how this is represented inside of a computer, just like with character sets and audio. We need to get these pixels into some kind of number so that we can convert it into binary and the computer can understand it. So as long as we understand that one pixel equals one square inside of a picture, then you should be okay. Now if you keep zooming into these pixels, what you'll find is that each pixel is a solid color. So one pixel equals one color. Now, obviously, I've zoomed in on this picture of a forest, and you can start to see the greens and the browns within the leaves and the tree trunk. But if you zoom in close enough, as you can see, each pixel is only one solid color. Okay, there's many different shades of green, many different shades of brown, but they are all one color. Now, when you zoom out, that's when you can see the image form. As long as we can understand that one pixel equals one color, then that should help you in the remainder of the lesson. So as we've mentioned, the graphics on a screen are made up of these tiny blocks called pixels. All these pixels joined together produce an image. Okay, the term pixel itself comes from the two words picture element. Okay, and it's just shortened into pixel. So with each pixel representing only one color, this makes it much easier to convert into a number because each color is represented by a numerical value. So in essence, each pixel is represented by a number, which can then obviously convert it into binary so the computer can use it. And it's as simple as that. Okay, you've got a bunch of colors down the bottom here, and each of these colors, each of these different shades of red, for example, will be a different number. Each of these different shades of orange, a different number. Okay, if you zoom in close enough, there's many different shades within each one, but each individual square will be a number. So this could be 4,285 of red, for example. But the more we go into this lesson, it'll make more sense as to why each pixel is represented by a number. Now, here are some more terms you might be familiar with. The terms 1080p, 4K, and even 8K. You might have seen these stickers at some point in your lives. You might see on the corner of a monitor or the corner of a TV. Now, if you didn't know, this just relates to the amount of pixels that this screen can display. Now we know what a pixel is, we should be able to understand that the more pixels visible on the screen, the better the quality is going to be. So more pixels is better quality. Just like with audio, the more samples we had, the better the quality of sound. The same with pixels. The more pixels we've got on display, the better the quality of the picture will be. However, just like with audio, the more samples you had, the bigger the file. Also with pictures, the more pixels we've got, more memory is needed to store the graphic, as more pixels means more numbers, which means longer binary. So this term resolution, which we're going to go into in a second, refers to these totals here. The resolution of an image is simply the width by the height. Okay, x times y here. So these total values are going to be very big numbers. An 8K television, for example, is 7,680 pixels across the bottom times 4,320 going upwards. So again, this will produce a very, very large number. In fact, if I just quickly work it out. Okay, so over 33 million pixels, which means 33 million tiny little blocks, all represented by color, which is represented by a number. Now, if we look at how technology has been developed over time, as you can see, graphics in games have gotten better, CGI in films has gotten better, because computers are able to handle more pixels. Graphics cards have got better, CPUs have gotten better, so the ability to process and develop these graphics with the use of more pixels has become possible. And as you can see, in the early versions of Mario, you can see that each individual pixel in the screen. And again, the same thing applies. Each block is one color. And as we've gone through time, the pixels become less evident and we have more of them in an image, so the images have become better. So we're going to strip it back now and go to the very basics. As we've discussed, computers only understand binary, so images need to be converted into numbers. Each pixel is given a binary value, and in this example, we're only having two colors. Okay, we've got black and white. So here you can see each pixel that is white is represented by a 0, and each pixel that is black is represented by a 1. Now this is really easy to follow because it's just one bit. So one bit is used to store either a 1 or a 0. As you can see here, we've got a little picture of a boat using only 2 colours, black and white. But as a stepping stone into learning this, each pixel is a number. And as you can see, they've started to build a picture by using these numbers. And that's where the term color depth comes in. Storing images in just black and white was obviously a thing of the past. And in order to introduce colors into our images, we had to allow more numbers to store these different colors in terms of each pixel using different colors. Now, the color depth is what we call the amount of bits available for each pixel. So the previous example only used a 1-bit color depth. The pixel was either a 1 or a 0. So only 1 bit was used to store the pixel's value. It was either 1 or 0. Now, if we double that amount and have a 2-bit color depth, that would allow for 4 different values. 2 bits in binary allows for these 4 values here. We've got 0, 0, which equals 0, 0, 1 equals 1, 1, 0 equals 2, and 1, 1 equals 3. So the same thing applies to our very first lesson in binary. We've got 4 different values. Now, these 4 values we can have as different colors. We have black and white from earlier, but we've also introduced dark grey and light grey. So although it doesn't seem much of a stepping stone, as we've discussed in previous lessons, these numbers can grow quite rapidly. So the more bits that we start to introduce, the bigger the numbers can get, and the more amounts of colours are available. So as an example, if we keep increasing the colour depth 1 bit at a time, the more colours start to become available. So 3 bits allows for 8 colours, 4 bits allows for 16, 32, 64, 128, and 256. Now, 256 colours is a lot more than what we've originally said, but it still wouldn't produce a very nice quality photograph. The 256 colours we'd have, we wouldn't have very many shades of each colour that would be involved. If we look at this example here, 256 colours in this example, you can see that the quality of the picture is quite grainy. There's not many shades of reds and blues and blacks. The quality just isn't that good. But as you can see in this one, 24 bits allows for 16 million colours, which obviously produces a decent quality photograph. And 24 bits, as it says there, is a typical colour depth of a photograph in today's world. 16 million colours is more than enough for the human eye to see, and it would produce a nice quality photograph. Now, something else we need to look at in this example, if we go back to the beginning here, 1 bit, black and white, so there's only black and white pixels available. In this example, only 2 colours produced a file size of 42 kilobytes. So the whole image for this, if it was just black and white, would be 42 kilobytes. When we increased the colour depth to 8 bits, we were then allowed 256 different values. Even though they are all within the grayscale, the quality did go up a little tiny bit. Still no colour, but the quality does go up. Now in this case, the file size has jumped from 42K to 320K. So it's gone up by quite a bit. But the point is, as you can see, the file size is starting to grow. If we look at the jump from 8-bit colour into 24-bit colour, we go from 420 kilobytes to 1.2 megabytes, which if we look at the pattern, 8 bits into 24, it's triple the size, and 420 times 3 is roughly 1.2. So the file size has tripled because we've introduced 3 times the amount of bits. So colour depth is just about how many colours you can use, how many bits available per pixel, how many different colours each pixel can represent. So now that we've discussed colour depth and resolution, we're now able to calculate the size of an image file. The formula, very similar to the audio, is simply the resolution multiplied by the colour depth. So the width of the image times the height times the colour depth will give us the answer in bits, and then we convert that into bytes and so on and so forth. So as an example, here we have a picture that's 1000 pixels wide and 800 pixels vertically and a 16-bit colour depth. So 16 bits available for the colours. And as you can see, it's a nice quality photograph. So the first thing we're going to do is we multiply the width by the height, which gives us 800,000. Then we take our resolution of 16 and we multiply those two values and we end up with 12.8 million. This answer is represented in bits. And to work this out into bytes, we simply divide it by 8 and that leaves us with 1.6 million bytes. So now we've got into bytes, we can easily convert into kilobytes by dividing by 1024 and again into megabytes by dividing by 1024 again. And the answer is 1.5 megabytes. If you were working into kilo or megabytes, you'd simply divide by just 1000. But in terms of the iGCSE syllabus, you are required to divide by 1024. Now, although you're not allowed a calculator in the exam, the numbers used should be easy enough to understand that you can simply do it on paper. But the formula is pretty simple to follow. Okay, the width times the height times the colour depth. And in an exam, you'll be given these values all you have to do is multiply them, get your answer in bits, go into bytes, and then into kilobytes and megabytes. So any image file that is made up of pixels is what we refer to as a bitmap image. Okay, a bitmap image consists of pixels. It contains tiny little blocks that are represented by a number, and that number represents a color. And typical bitmap image file types include these here. You might have seen these before if you've done any photo editing or have access to a camera, but these file types here are all types of bitmap images. So we've got BMP, JPEG, GIF or GIF, PNG, and TIFF. Okay, so these all are made up of pixels. There are also images called vector graphics, which are made up of lines and squares and shapes, and they don't contain pixels. They are made up of instructions and measurements to simply draw a picture. So this file here, for example, you can see it's got instructions to draw a semicircle, and this image wouldn't comprise of pixels. So vectors are useful for things like logos and fonts, and typically graphics where you would need to print them on a large scale. As you know, with a bitmap image, if you zoom in enough, you will start to see the pixels. So for example, if you took a picture on an iPhone and wanted to print it onto a huge canvas, it's not going to be crystal clear quality. However, a vector graphic would, but as it doesn't contain pixels, it's not typically used for photographs. It's typically used for graphic design or, like I said, logo design, just basic shapes. So just to finish off, as always, you've got some basic questions here. Give the video a pause and then resume to check your answers. A bitmap graphic is made up of pixels. Each pixel is represented in binary. The something determines the number of available colors for an image. This was called a color depth. And the greater the something and something else of the image, the greater the file size. So this will be the resolution and the color depth. The more pixels we have and the higher amount of colors available to each pixel, the file size will increase. And just to confirm, there's the answers there. There is one more lesson in Unit 1, and it's all about compression, file compression. And then what will follow after that is a Unit 1 topical question paper that I will go through some typical exam style questions, and that video will follow after the final video of compression. So as always, guys, I hope you managed to follow along, and I will see you in the next lesson.